So in today's session, we will be doing section 4.5, dimension. So this is the last topic for our course. Let us recall this definition. A vector space V is said to be finite dimensional if V can be spanned by a finite number of vectors in V. If no finite numbers of vectors that can span V, then we say V is infinite dimensional. So previously we had several examples of finite dimensional vector spaces and also an example of infinite dimensional vector space. So for the finite dimensional, let's say you have your R2, okay, or R3, or even Rn, the more general Euclidean space. And then we also had the space of n by m matrices, okay? Or maybe the space of square matrices, okay? So these are both finite dimensional. On the other hand, recall the space of functions that are defined on the interval negative infinity to plus infinity, right? So this is infinite dimensional, okay? This is infinite dimensional. And also coming from this space, a subspace of this capital F, we have defined another finite dimensional space, okay? So you have your space of polynomial, okay? Space of polynomials of degree at most n. So this is denoted as like this. This guy here, this is finite dimensional, okay? So these finite dimensional spaces in here, we've seen that each of them can be spanned by a finite number of vectors, okay? So all bases for a finite dimensional vector space have the same number of vectors, okay? So recall the definition of a base. We say that a set forms a base if that set spans the vector space and also that set is linearly independent, okay? So if we found two bases for a particular vector space, then we say, then we should have the same number for each set. Meaning, for example, if we look at the space R2, okay? So in the space R2, we know that the standard base 1, 0, comma 0, 1. This is the standard basis for R2. This has two elements. If we check this set here, 1, 0, comma 1, 1, I think we've seen in the previous lecture that this is also a basis. So this has two elements, okay? And maybe you can also check this set. This also forms a basis for R2 and it has two elements also, okay? For example, another example, if we look at P2, so this is the space of polynomials of at most degree 2. The standard basis is 1, x, and x squared. So this has three elements. We can get another basis for this. say we have 1 plus x, 1 plus x squared. So again, this is a basis for P2. You can check that this forms a basis. And um, it has also 3 elements. Okay? So the basis for P2 always uh, always have 3 elements. Okay? And so on and so forth. You can also use your space of matrices. If you have n by n matrices, then the number of elements in that n by n, the number of elements in the basis of that n by n, space of n by n matrices is n squared. Okay, maybe let's write that. For example, let us consider M22. Okay, so a standard basis for this, you have your 1 0 0 0. Okay, here you have 0 1 0 0, and then you have 0 0 1 0, and then you have 0 0 0 1. So this is the standard basis for this space. And in one of the exercises that we had last meeting, we found another basis for M22. Okay, so it has um, one on this entry and everything 0, and then 1 1 0 0, then 1 0 1 0, and then you have 1 0 0 1. So that again forms or that those elements form a basis for the space M22. So we've done that on last meeting. So anyway, the point of this theorem is that if we found 2 bases for a vector space, then those 2 bases have the same number of elements. Okay, so here are those examples. So for the R3, you have here the standard basis, and this guy here is another basis for R3. Okay, for M22, okay, this is the one that I discussed in the previous slide. So we have the standard basis, and then this guy here is another basis. Now, since the number of elements in a base, okay, of a vector space are all the same, okay, then we must give a name for that. Okay, so here we define the dimension of a finite dimensional vector space. So the dimension is just the number of vectors in a basis for B. Okay? Since if you take any basis, the number of elements in that will be the same as the number of elements of another basis, meaning it remains constant. So you must give a name for that. So we call it the dimension. Okay? Now, for the zero vector space, we define it to be to have a dimension 0. Okay? So the zero vector space is defined to have a dimension 0. So for example, the dimension of R3, that the Euclidean space R3, so this is 3. That's why I always say this is the 3-dimensional space, and R2 I always say it's the 2-dimensional space. Now, the dimension of M22, we've seen that it has that a basis has 4 elements. So the dimension of M22 is equal to 4. And then for this, the dimension of Pnx, the space of polynomials of at most n, of at most degree n, okay, it's n plus 1. So if you don't remember, the basis for this p sub n, this is 1 x squared until x to the n. So from x to the n, that's n elements. and then you have this constant 1. So you have n plus 1 elements. So that's the dimension of Pn of x. Questions so far? For the following theorem, okay, let V be an n-dimensional vector space. Now, if a subset of V has more than n vectors, then it is linearly independent. Okay? If a subset of V has more than n vectors, it is linearly independent, meaning you can always get at least one element from that subset, and you will be able to write it as a linear combination of the other elements. Okay? Next, if a subset of V has less than n vectors, okay? So if a subset of V has less than n vectors, then it does not span V, okay? So meaning if you have n minus 1 vectors, you cannot get, if you take the span of that, you cannot get the entire vector space V. Okay, so take note for a basis. So basis, okay, if S is a basis, or S is a basis, a set S is a basis. So a set S with n vectors, okay, so V1, V2 until Vn is a basis, for a vector space V if and only if, so we just recall this, if and only if one, S is linearly independent, okay, and number two, if span of S, this is equal to the vector space V. So this is the definition of basis. Okay, so S has n vectors. If you have more, then definitely that set with more than n vectors will be linearly dependent. Okay, and if you are missing some elements, you have less number of elements than the set S, okay, then it cannot span the vector space V. So we will not prove this. Just remember these two statements. Okay. Now, for example, find the basis for and the dimension of the solution space of the following homogeneous system. So recall that if you get the general solution of a homogeneous system, then you will be able to get the solution space. And we mentioned last time that the solution space forms a vector subspace of Rn. So in here you have 1, 2, 3, 4 equations, and you have 6 unknowns. Okay, so the underlying space in here is R6, coming from the 6 unknowns. So let us check the basis for the solution space of this, and therefore once we know the basis for the solution space, we will be able to get the dimension of that solution space. So we start by solving for the general equation of this homogeneous system. So let's do Gaussian elimination maybe. Okay, since this is not a square matrix, So let's do Gaussian elimination. Besides, even if this is a square matrix, you will still have to get the general solution. So you will need to use Gaussian elimination or Gauss-Jordan elimination, up to you. Okay? Or maybe you use you get the matrix of coefficients, and then you get the reduced row echelon form of that matrix of coefficients. Okay, maybe let's use that one. We get the matrix of coefficients of this linear system, and then let's find the RREF of that, and then we convert again to the equations to get the solution space. So for the matrix of coefficients, okay, you have 2, 6, -5, -2, 4, -3. So you have 2, 6, -5, -2, 4, -3. For the second one, we have 1, 3, -2, and then you have 0, and then +2, and then 0. For the third, you have 0, 0, and then 5. So 0, 0, 5, 10, 0, 15. Then finally, you have here 2, 6, 2, 6, 0, 8, 4, 18, 4, 18. So here we have the matrix of coefficients. We find RREF. Okay. So let's do operations here. So let's just, well, since this is already 1, let's just interchange the 2. Okay. I don't want to divide the first row by 2 because if we have -5/2 or yeah, -3/2, you'll have some fractions, and later on it might make our computation not easy because of the fractions. Okay, well, it's really not easy, but you have fractions, so it will make the computation more complicated. So what we're going to do is to interchange first row and second row. So row 1 interchange with row 2. So row 1 now, row 1 becomes 1, 3, 1, 3, -2, 0, 2, 0. Row 2 now, it's 2, 6, -5, -2, 4, -3. Row 3 is still the same. You have 0, 0, 0, 5, 10. Sorry, 0, 0, 5, 10. So 0, 0, 5, 10, 0, 15. And then row 4, you have 2, 6, 0, 8, 4, 18. Okay. And then this is a leading one. Let's make this 0, and then this guy here 0. So we can have row 2 minus 2 row 1. And then also we can have row 4 minus 2 row 1. And then if you see row 3 here, you have 5, 10, 15, and then the other elements or the other entries are 0. So all the entries in row 3 are divisible by 5. So let's divide row 3 by 5. And take note that it is independent of these two operations here, so we can do that. So row 3 divided by 5. So in here, we just copy row 1. You have 1, 3, -2, 0 to 0, 0 to 0. For row 2, so row 2 minus 2, row 1, so 2 minus 2 there, that's 0. 6 minus 2 times 3, that's 6 minus 6, this is again 0. -5 minus 2 times 2, 2 times -2, so -5 plus 4, that's -1. -2 here, and then 4 minus 2 times 2, that's 4, so 4 minus 4, that's 0. And then you have here -3. And then for row 3, we are just dividing by 5. So you will have 0, 0, 1, 2, 0, 3. Oh, this is nice. And then row 4, we have row 4 minus 2, row 1. So 2 minus 2 again, that's 0. 6 minus 2 times 3, again, that's 0. And then here, 0 minus 2 times -2, that's positive 4 in here. 8 minus 0, that's just 8. And then 4 minus 2 times 2, again, that becomes 0. And then you have your 18 minus 0. So you have 18. Okay? So for this, notice we can actually what? Row 3 here, it's the same almost as row 2. You'll just have to negate this. So this will disappear in a while. While for this guy, row 4, okay, for row 4, let's just subtract or add row 4 plus 4 row 2. Okay, so let's retain first row 2. Okay, and then let's just add row 3 plus row 2. And then for row 4, we will have row 4 plus 4 row 2 plus 4 row 2. So at this step, we are not changing the signs here in row 2. So we are retaining it first. We'll do the change later on our next step. Okay? So for row 1, we have 1, 3, -2, 0, 2, 0. For row 2, we have 0, 0, -1, -2, 0, -3. For row 3, it's entirely zeros. Okay. And then for row 4, you have 0, 0 on the first two entries. And then you will have 4 plus 4 times -1, that becomes 0. 8 times 4 times, sorry, 8 plus 4 times -2, that's again 0. Then of course 0 plus 0. And then in here, 8 times 4, 8 plus 4 times -3. So 18 plus 4 times -3. So 18 minus 12, that's 6. Okay. So we have this, and we're almost done. We just have to make this 0 here. Okay. And then we just convert this to, particularly this entry, we need this to be +1. And then this guy here, let's just divide it by 6. Okay, so let's do that. Let's first make this 0. Okay, Let's make that 0. So let me copy. Mhm. So we are here. Okay. So for this, we want to make this 0. So we will have row 1 minus 2 row 2. And then our row 4 will be divided by 6. So row 1 minus 2 row 2, you have 1 minus 0, that's still 1. 3 minus 0, that's still 3. And then minus 2 minus 2 times negative 1, so that becomes minus 2 plus 2, so that becomes 0. And then 0 minus 2 times negative 2, that becomes 4. Correct? 0 plus 4. So this is 4. 2 minus 0, that's still 0. Then 0 here. Um, 0 here minus 2 times negative 3, that's positive 6. Okay? And then what do we have in here? You have 0, 0, negative 1, negative 2, and then 0, negative 3. And then you have 0, 0, 0, 0, 0, 0. And then you have 0, 0, 0, 0, 0, 1. Okay? Then let's put this 0 row at the bottom. So let's interchange row 3 and row 4. Row 3 interchange with row 4. And then let's remove the negatives in here. Particularly this negative 1, we turn it to positive 1. So we have negative row 2. So we will have 1, 3, 0, 4, 0, 6. And then you will have 0, 0, 1, 2, 0, 3. And then we will have 0, 0, 0, 0, 0, 1, and then the 0 row in here. Okay? For the last step, we make this 0 and we make this 0. And that becomes the RREF. Okay? So we have row 2 minus 3 row 3. Also, we have row 1 minus 6 row 3. So row 2 minus 3 row 3. And then row 1 minus 6 row 3. So let's do row 1 minus 6 row 3. So everything on the first 5 entries we'll just copy. And then this guy here, 6 minus 6, that becomes 0. So we have 1, 3, 0, 4, 0, 0. For row 2, we copy the first 5 entries. And then the last entry will just be 3 minus 3. So 0, 0, 1, 2, 0, 0. Then, of course, row 3 will just copy that. And then here you have the 0 row. So this is the RREF. This is in reduced row echelon form, as you can see. Okay, this is a leading one, all other entries are 0. Here, this is also a leading one, all other entries in its column, okay, to be more precise. So leading one, all other entries in its column, it's 0. Also this guy here, and also this guy here. Okay. Therefore, okay, let's again copy this guy just to have a reference on next page. So you have this. Okay. So the general solution is so you have this, okay? Oh, let's not write the general solution first. Let us convert this to equation form, and then we write the general solution afterwards. So you have x1 plus 3x2, and then plus 4x4. This is equal to 0. For the second equation, we have here x3 plus 2x4. This is equal to 0. And then for the third equation, we just have x6 equals 0. Okay? Which means we have fixed x6. It's always 0. Okay? And then in here, we can have a variable for x4, for x2, and then for x5. You don't see any x5 in here. So it can take any number. Okay? So we have let x2 be equal to s. Let's use s. Or r. Let me just use r. Let x2 be equal to r. x4 be equal to s. And x5 be equal to t. Okay. Then we have x1. This is equal to, so we bring this to the other side, and then this guy here also to the other side. Okay. So x1 equals negative 3r minus 4s. And then for x3, this is equal to minus 2s. And then, of course, you have your x5 equals t, and x6 here equals 0. Okay? So x6 equals, let's put the 0 in here anyway. Okay? So this is the general solution. So how do we find the basis and the dimension of the solution space? So coming from this, we rewrite the general solution in vector form. Okay? So we rewrite it in vector form in vertical. So you have x1, x2, x3, x4, x5, and then you have your x6 in here. Okay. And then our x1 was minus 3r minus 4s. So minus 3r minus 4s. Our x2 was r. Okay. Our x2 was r. x3 is minus 2s. x3 it's minus 2s. x4 was s. x5 was t. Let me put it here. And then x6, it's just 0. Okay. Or simply, this guy here, what we can do is we can separate each letters here, R, S, and T, and of course the constant part. We separate that, and then we factor out the letters. And we will see the vectors that will give the solution space, okay? Or that will give the elements for the basis of the solution space. So in here, you will get negative 3, 1, 0, 0, 0, 0, and you multiply this to r. You see this? You have r in the first row, r on the second row, and then nothing, no r on other rows. That's why you have here 0. Plus, for the s, we have here negative 4 on the first row, 0 on the second row, then negative 2 on the third row, positive 1 on the fourth row, and then 0, 0. And then you have here s, plus for the t, we just have t on the fifth row. Then everything else is 0. So you will have 0, 0, 0, 0, 1, 0. And then this is your t. Okay? But here, r, s, and t, these are just real numbers. So basically, this is already of the form of spanning set. Okay? And therefore, these vectors here, this vector, this vector, and this vector, these three vectors will actually be the elements of the basis for the solution space here. Okay? So therefore, the solution space, the basis or a basis for the solution space is, we'll just copy those vectors. You have negative 3, 1, 0, 0, 0, 0. And then you have negative 4, 0, negative 2, 1. So negative 4, 0, negative 2, 1, and then 0, 0. And then the third, you have 0, 0, 0, 0, 1, 0. So this guy here forms a basis. And therefore, since we have only 3 elements, the dimension is equal to 3. So the dimension of the solution space is 3. Okay? questions? Okay. Okay. So let's consider this theorem. Let V be a finite dimensional vector space and let W be a subspace of V. So remember, um, if you have a vector space V here, okay, so V, this is a vector space, and you get another, or you get a subset of V, we name it W, and it turned out that this is also a vector space, okay, then your W, this is a subspace of V. Remember this symbol? In here we say it's subspace, okay? But the point here is your W is just inside V, okay? Now, if the bigger vector space is finite dimensional, therefore, or then the smaller, okay, the subspace which is inside that bigger vector space will also be a finite dimensional, okay? So V is finite dimensional, the one smaller will also be finite dimensional. And of course, the dimension of W cannot exceed the dimension of V. So the dimension of W will be less than or equal to the dimension of V. And V equals W if and only if they have the same dimensions. Okay? So W equals V if and only if dimension of W equals dimension of V. Take note that your W here, it's a subspace of V. Okay? This is an if and only if. Okay? Your W equals V if and only if dimension of W equals dimension of V. If you break this down into two parts, if W equals V, then the dimension of W equals dimension of V. The second part will be, if the dimension of W equals dimension of V, then W equals V. But again, keep in mind that your W is a subspace of V. Okay? Take note of that condition here. If you remove this condition, okay, if you remove the fact that W is a subspace of V, then the direction, this part implies this part, may not be true. Okay? Meaning, if you get two vector spaces with the same dimension, it doesn't mean they are the same vector space. Okay? For example, so let me add this note. Note for item 3, okay? This guy here, if W equals V, then dimension of W equals dimension of V. And then for the other guy, okay, if dimension of W equals dimension of V, take note of this additional, and W is a subspace of V, then W equals V. Okay? This part here and W is a subspace of B, it's coming from the main statement here or main assumption here. If you remove this part, then the equality may not hold. Okay, so example. Okay, without the assumption star, let me put this assumption here as the assumption star. So without the assumption star, okay, conclusion may be false. Okay, for example, your P2 of X, and then you have your R3. Okay, dimension of P2, okay, of X, this is equal to 2 plus 1, which is 3. That's your n plus 1. And of course, you know that the dimension of R3, this is equal to 3. So these two guys here, they have the same dimension. Okay, they have the same dimensions, but they are not equal. So take note of that. Dimension of W equals dimension of B, then W equals B. So without this condition, okay, without this condition, this will be false, or this may be false. So, but P2, this is not the same as R3. Oops, but okay. Questions? For this statement here, you see I didn't have to add this condition. It doesn't matter now because they are just the same vector space. Definitely they will have the same dimension. So with or without this condition here, because W equals V, the dimensions will be the same. Besides, if W equals B, W will be a subspace of V, trivially. Okay? Questions? Okay, so let's have this example. Consider the vector space V, which is R3, in the usual operations. So meaning usual addition of vectors and scalar multiplication. Let W be the span of this. Okay, let W be the span of these two elements. And it is a subspace containing all linear combinations of this guy here. Since this W here is just a subspace of R3, okay, then the dimension of W is less than or equal to the dimension of R3. But the dimension of R3 is equal to 3. Okay? In fact, you can show that the dimension of W is equal to 2. So here, in fact, dimension of W, this is just equal to 2. Okay? Now, the dimension here of W, I said it is equal to 2. It's not because it has two elements. Okay? You still need to show that these two guys here are linearly independent. Okay? you need to show that these two guys here are linearly independent. Once you've shown that they are linearly independent, then that's the time you can say that the dimension of W equals 2. Okay? Is that clear? So you still need to show linear independence for these two guys. Okay, so next problem here. Given this W, which is a subspace of P3, let us determine the basis and the dimension of this subspace W. So W, of course, subspace of P3, so it's a set of polynomials of at most degree 3. Okay? Such that when you evaluate P at 1, okay, and you evaluate P at -1, they are both 0. Okay? So, first, let us write these conditions here. Okay, or let us write the form of the elements of this space W. Okay, so let P of x, which is a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x, a sub 3x cubed, be in W. So we are getting an element from the space W. The W has this condition on its elements. Therefore, then your P of x, you can factor this into the following. You can factor this into x minus 1, x plus 1, and then you have your a3x plus r. Correct? How? Of course, if you multiply these three polynomials here, x minus 1, x plus 1, a3, x plus r, this will give you a polynomial of degree 3. Okay? Now, how did we get this x minus 1, the factor x minus 1? It's coming from this. P of 1 equals 0. Okay? So as you can see, if you let x equals 1, this will give you 0. So whatever these guys are, it still be 0. And then the x plus 1, similar situation or similar explanation. The x plus 1 came from this condition. P of -1 equals 0. So if we replace our x with -1, because of this x plus 1, okay, this product here will be equal to 0. So this guy, again, x minus 1 came from this condition, P of 1 equals 0. X plus 1 came from this condition, P of -1 equals 0. What about this a sub 3x plus r? It came from, of course, after factoring this x minus 1, x plus 1. And it's a general polynomial now. To be more precise, it's a general linear function or linear function. Okay? So, from here, we will get, what we're going to do is to distribute this x minus 1 and x plus 1 over this sum in here. So we will see a3x times x minus 1, x plus 1, plus r times x minus 1, x plus 1. Okay? Yes, question? Unmute yourself.
Yeah, sorry.
Yeah.
I don't understand how we went from the first to the second line.
We just distributed this. So we fix this x minus 1, x plus 1, and then we distribute it to this plus to this. It's just distribution.
No, not the third line, from the first line to the second line.
This guy to this guy.
Yeah.
Well, first, you have these polynomials. These are the form of all the polynomials in W. Okay? It's a at most third degree polynomial. But since you got P of X to be in the space W, it must, this polynomial here must satisfy these conditions.
Okay.
This condition tells us that you must have x minus 1.
Why does it tell us to have x minus 1? It only tells us that p1 equals 0.
Yeah, because from your basic algebra, okay, from basic algebra, okay, P of X polynomial, if P of R equals 0, then x minus R is a factor, is a factor of P of X. Okay? Meaning, you can take out that x minus R because that's just the only way to have this P of R equals 0. Okay? By P of R is a factor, meaning your by x minus R is a factor of P of X. Your P of X, this means you have your x minus R times whatever this guy is. Okay? The presence of x minus R here gives us this part here. Take note. So if this is your P of R or your P of X, okay? P of R, this is equal to R minus R times whatever this guy here. This is R minus R, it's 0 times whatever this guy here. This is equal to 0. So without this x minus R, then meaning if you cannot factor the x minus R, then you won't have this part here, your P of R equals 0. Because this polynomial will not be equal to 0 if you cannot factor out the x minus R. So in this case, P of 1 equals 0, you must have the factor x minus 1. If you cannot factor the x minus 1 in here, then your P of 1 cannot be 0. Okay? In fact, this guy here, this statement here, it's an if and only if statement. So P of R equals 0 if and only if x minus R is a factor of P of X. Okay? So it's from basic algebra, maybe college algebra or your Sec 4 or Sec 5. I don't know which secondary math will give you this part. Either Sec 4 or Sec 5. Okay? So that's what we have. From this condition, P of 1 equals 0, you must have your x minus 1. P of negative 1 equals 0, you must have your x plus 1. Because again, if you evaluate P at negative 1, this guy will not be 0. This guy will be 0. This guy, we don't know if it is 0, but whatever. Since this guy here is 0 already, then everything will be 0. Okay? So if we distribute this x minus 1, x plus 1 to the sum here, you will get this guy. Okay? So now, look at this. A sub 3, it's any real number. In fact, it's the coefficient of your x cube in here, but this is arbitrary. So basically, your A sub 3, this is any number. Your R, it's also any number. Okay? So this guy here, we can write this as some A sub 3. Let me write this P sub 1 of x plus you have here R P sub 2 of x, where P sub 1, of course, this is your x times x plus 1 or x minus 1 times x plus 1. So this guy here, x minus 1, x plus 1. And of course, your P sub 2, it's this guy here. P sub 2, this is your x minus 1, x plus 1. And in here, you can verify that P1 and P2 are linearly independent. Okay? So note P1 is of degree 3. Oops. While P2 is of degree 2. So P1 and P2 are linearly independent. P2 are linearly independent. Okay? And take note, P, it's a polynomial in W. It's any polynomial in W. And this guy here, this last equation here tells us that W is actually a span of P1 and P2. Okay? So since P of x is arbitrary, okay, W becomes span of P1 and P2. And let us write that P1 and P2, or those P1 and P2. So our P1 is x times x minus 1, x plus 1, comma, P2 it's x minus 1, x plus 1. So this part here has two elements only, P1 and P2, and we are looking at the span, okay? And this guy, these two elements here are linearly independent, okay? So these two guys here, or these two guys here form a basis, okay? And since they form a basis, we now have the dimension. We now know the number of elements, okay? So dimension of W will be equal to 2. Okay? Questions? Next. So here, this time we are given a subspace of M22. So let W be this space or be this set satisfying this condition. So be the matrices A, B, C, D with this condition. And take note here, D is any real number. So we want to determine a basis for and the dimension of the subspace W. So again, we start with an element of W. So let A, B, C, D be an element of W. Since it's an element, this guy here is an element of W, this condition must be satisfied. Okay? Then you have A minus 2B plus, A minus B plus 2C. This must be equal to W, and your D is any real number. Or from this, you can write A equals B minus 2C. So let us rewrite this. Let us rewrite this matrix. So you have the matrix A, B, C, D. We replace A by this guy. So B minus 2C, and then B, C, D. And then we just separate all those with a B, all those with a C, and all those with a D. Particularly, we have here B, B, 0, 0 plus minus 2C, 0, C, 0 plus you have 0, 0, 0, D. Okay? Following so far? And then from here, you can factor out the B because there are no other letters in this matrix. Here you can factor out the C. There are no other letters in this matrix. Here you can factor out the D. And no other letters in this matrix. So you will have 1, 1, 0, 0 times B, plus in here you will have negative 2, 0, 1, 0 times C, plus in here you have 0, 0, 0, 1 times D. So B, C, and D, these are just real numbers. Now, every matrix A, B, C, D can be written in this form. And you can check that these three matrices here, this, they form a linearly independent set. Okay? So, verify that that set or the set containing these vectors here 1 1 0 0 comma negative 2 0 1 0 and comma 0 0 0 1, verify that this set is a basis for W, basis for W, meaning they are linearly independent. And of course, they span W. The span of W, it's already um, it's already written in here. This is an element of W, and then you can write it this way. So it remains to show that these three vectors are linearly independent. So once you've verified this, you can now conclude that the dimension of W, this is equal to 3. Okay? Questions? Okay. Now, let's look at this theorem. So let S be a non-empty set of vectors in a vector space V. If S is linearly independent, okay, and if V belongs to the vector V and does not belong to the span of S, okay, then the set S union the set containing V, meaning you put your V inside S, okay, that new set is still linearly independent. Okay, so let's see. Let's just look at the set. So you have the set S. You have the set S. Say you have V1, V2, etc. until Vn. Okay, and then S union the set containing V. This is just your V1, V2 until Vn. And then you also include V. So it's a new set. Okay? So this theorem tells us S, so this set here, It's a linearly independent set. And the element V, okay, the V does not belong into the span of S. Okay? So meaning you cannot write V as a linear combination of V1, V2 until Vn. Then this set here is still linearly independent. Okay? Take note that the vector space V does not say that the dimension is n. Okay? Now, if V is a vector in S, and V can be expressed as a linear combination of the other vectors in S, so this time, you started with this set, okay? So in here, this time you started with the set V1, V2 until Vn, and then you have your V, okay? And also, V belongs to the span of S. Oh, sorry. V belongs to the span of the set V1, V2 until Vn. So V can be expressed as a linear combination of other vectors in S. So your S is this guy. It contains V also. But V is a linear combination of the other vectors. So it belongs to the span of V1, V2 until Vn. Okay? Then, the span of S, so this S, it contains V, it's also equal to the span of this guy. It's the set S without the V. So, this guy here, it's precisely this guy here. So, it's the set S without the V. Okay? Okay? For example, let's look at some um, simple example here. Let's look at R3. We let our S to be the set 1, 0, 0, and then 0, 1, 0. So S, definitely this is a linearly independent set. Let me write here number 1. So I am referring to the first statement here. Okay. And then you let your V be the element 0, 0, or maybe 0, 1, 1. Take note, you have S 1, 0, 0, 0, 1, 0. The span of these two guys, the third component is always 0. Your vector V, the third component, it's 1. So definitely here, V does not belong to the span of S. Okay? S here, it's linearly independent. Okay? It's a linearly independent set. V does not belong in the span of S. This means that your S union the set containing V. This set, it's just 1, 0, 0, 0, 1, 0. And now with the V, you have 0, 1, 1. This guy here is still linearly independent. Okay? Questions? Okay? For number 2, let's look at up here. For number 2, still let us use R3. Okay? So this time our S, let's take these elements 1, 0, 0. Let's have 0, 1, 0. And then you have here 2, 1, 0. Okay? Let's use V to be 1, 0, 0. So we have the set S. We take this as our V, 1, 0, 0. Okay? And let's see. We can rewrite this. We can write 1, 0, 0 in terms of these two vectors. Okay? If we try to do that, this is just 1 half 2, 1, 0 minus 1 half 0, 1, 0. 0, 1, 0. So 1 half times 2, 1, 0, this becomes 1, 1 half 0 minus 1 half of this. So this becomes 0, 1 half 0. So the middle, it becomes 1 half minus 1 half. So that becomes 0. The first entry, 1 half times 2, that's 1, minus 0, that's 1. And of course, that the third entry here, 0 and 0, it's still 0. So we have a set S, we have a V in S, and V can be written as a linear combination of the other two vectors. So this theorem tells us that if you get the span of S, so the span of S, this is still equal to the span of S minus the set containing V. Or the span of the set 1, 0, 0, 0, 1, 0, and 2, 1, 0. This is still equal to the span of 0, 1, 0, and 2, 1, 0. So this is what the second statement here is telling us. So you have a set S, you have a vector in that set S, which can be written as a linear combination of the other vectors. If you remove it, you still get the same span. Okay? Questions? Next theorem here. let V be an n-dimensional vector space. So this time we have an n-dimensional vector space. And let S be a subset of V with exactly n vectors. Okay? So here S has exactly n vectors, and n is the dimension of V. Then S is a basis if and only if S is linearly independent or spans V. Okay? Meaning, to know or to show that S is a basis, you only need to show one of these. Okay? Remember, again, we go back to the definition of uh, the basis that I already wrote in this part here. Okay, let's copy this and bring it to that page. So you have here, a set S is a basis for V if and only if you got these two. Okay? This time, dimension of V is equal to n. Okay? So dimension of V equals n. The number of elements in the set S is also n. Okay? The theorem says you can just check this guy or this guy. S is a basis if and only if S is linearly independent or spans V. Okay? So here still S V1, V2 until Vn. Okay? S is a basis. So to show that S is a basis, okay, one only needs to check one condition, one of the two conditions. Conditions above. Okay? So meaning you don't have to check both, just one. But again, these conditions or these hypotheses must be satisfied. Your V, the dimension of V is n. Your S must only contain exactly n elements. Okay? Questions? So for example, let's look at one example here. In R3, okay, let's use polynomials. In P2, P2x, okay, dimension of P2x, this is equal to 3. Okay, so let us look at the set S. Suppose this set X has these elements. We have, let's take 1, and then let's take 2 minus x, and then let's take x plus x squared. So the dimension of P equals 3. S has 3 elements. To show that S is a basis or not, we only need to check one of these two statements here. Okay? So choose which one is the best, or choose which one is easier to show. Okay? Maybe we can show linear independence. Okay? So to show linear independence, so to show linear independence, um, suppose you have k times 1 or k1 times 1 plus k2 times 2 minus x plus k3 times x plus x squared. Suppose this guy here is equal to 0. Okay? Let's convert this into a matrix form or a system of linear equations form first. So for the constant part, we have k times 1, k1 times 1, so you have k1. And then here you have k2 times 2 here, plus 2k2. Here we don't have any constant, so we don't have a k3 part, but this is equal to 0. For the linear part, this does not have a linear part. This we have a linear part, so k2 times negative x. So we have negative k2 here. Here we also have a linear part, it's k3 times x in here. So plus k3, this is equal to 0. And for the squared part, this does not have a square part. This does not have a square part. This guy, we have k3 times x squared. But we only have here k3, and this is equal to 0. This third equation, well, it says k3 equals 0. Okay? So we got this. And if we use this, from second equation, we will have k2 equals k3, but k3 is already equal to 0. So k2 is also equal to 0. And then from the first equation, we will have k1 equals negative 2k2, but k2 is equal to 0 now. So this is equal to 0. Okay? So all these coefficients here, all these scalars, k1, k2, and k3 are 0. So this set is linearly independent. Okay? So just write that conclusion. Suppose this is true, we solve, therefore, this is linearly independent. And therefore, this is a basis. We don't need to do the span. So we are using this theorem here. Okay? Questions? Next theorem here. Let S be a finite set of vectors in a finite dimensional vector space. If S spans V, but is not a basis for V, then S can be reduced to a basis for V by removing appropriate vectors from S. And then the second, if S is linearly independent but not a basis for V, then S can be enlarged to a basis for V by inserting appropriate vectors into S. Okay? So what does this mean? So for number one, you have a vector V, you have a set S, okay? You have a set S, say this set S has R elements, V1, V2, until VR. And in here S, or the span of S, this is equal to the vector space V. Okay? But S is not a basis, but S is not a basis. So the first statement here, it says you can remove some elements in S. Okay? You can remove some elements in S to form a basis for V. So let me write this, not a basis for V. So one can remove elements from S to form a basis for V. So meaning you can have, say, V1 until VR minus 1. So you removed one of the vectors. Okay? And then once you have removed something, check if it is a basis. Okay? If it is not a basis, again, remove another one. If it is already a basis, then you stop. Okay? For example, let's look at this. E.g., again, let's look at R3. So let S be equal to the vector 1, 0, 0, or let S be the set containing the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, and then you have here 1, 2, 6. Okay? Take note of this. R3, the dimension of R3 is 3. S contains 4 elements. Okay? So this cannot be a basis. The basis must only have 3 elements because your dimension is equal to 3. So this guy here, the span of S, this is still equal to R3, but S is not a basis. Okay? So we remove one element from S. So now, let's say we remove the element 1, 0, 0. Okay? S, the new S, let me write this as S prime. Here you have 0, 1, 0, 0, 0, 1, and then the third element it's 1, 2, 6. you can check that this S prime is a basis. It has 3 elements. It's equal to the dimension of R3. Then check, is this linearly independent? If it is linearly independent, then this S prime is a basis. So that's the first statement. S can be reduced to a basis for V by removing appropriate vectors from S. We have the S, 4 elements. It's not a basis. We remove one element. So let's rename it as S prime. This has 3 elements. We need to check if this is a basis or not. You can just use linear independence. And once you've checked that it is that the elements are linearly independent, then this is a basis. So that's the first statement here. For the second statement, okay, so you have a linearly independent set, but not a basis for V. So you have S, V1, V2 until VR. This is linearly in depth. Okay, but so linearly in depth, but not a basis for V, but not a basis for B. Okay, then take a vector, take an appropriate. Let's write that word. Take an appropriate vector V. Okay, insert in S, insert this in S, insert this in S. Okay, once you've inserted this in S, check if it is still linearly independent and if it is now a basis for B. So that's what the theorem number 2 here says. Okay, so show S union dot V, because you need to insert it. Show that the set V1, V2 until VR, comma V is still linearly independent. Check if this is still true. And check also that the span of S union V now is equal to capital V. Because if you have now these two guys, then this new set is a basis. So that's what second theorem is telling us. S can be enlarged to a basis for V by inserting appropriate vectors into S. For example, let's look at let's look at M22. Okay, M22. And then let's have S. So we have M22. Let's have S to be the set containing the following matrix. So 1, 1, 0, 0, 1, 0, 1, 0, and then you have here 1, 0, 0, 1. Okay? This guy here linearly independent. Okay? And since you know that the dimension of M22 is equal to 4, so in here, dimension of M22, this is equal to 4. And this set S only has 3 elements. This is not a basis. Not a basis. Okay? Then maybe take V equals 1000. You can insert this. Insert in S. In S. So now your S prime, this is the set with elements 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, and now you insert that V, 1, 0, 0, 0. This guy here, you can show this is a basis. In fact, we've shown that this is a basis. Okay? So that's what Theorem 2 says. You have a vector space, you have a linearly independent set, which is not a basis. You can enlarge it by inserting some appropriate vector. And then show that after the insertion, show if it is a basis. If it does, then we are done. If not, insert another element. But every time you insert some element, you have to check if it is a linearly independent set. Well, you have to do that because you want to show that it is a basis. Okay? Questions? Okay. Now, let's look at this example. In fact, this is not an example. It's actually more results. So suppose let's take V1, V2 until VR, be vectors in a vector space V, and let W the span of V1, V2 until VR. Then the dimension of W will be less than or equal to R. Okay? It's not necessarily R because maybe one of the vectors can be written as a linear combination of the other vectors. That's a possibility. If you look at this, correct? If you look at this, you have the span, okay, but not a basis. So you have to remove something. Okay? Or maybe you look at the previous theorem that we had in here. I think it's this guy here. You got the linearly independent. Oh, you got a vector S and V is in S, and V can be expressed as a linear combination of the other vectors in S. So the span of S is equal to the span of S minus V. Okay? So that's the reason why we still have less than symbol here. Because there's a possibility that one of the vectors in this set is a linear combination of the other vectors. However, if the set V1, V2 until VR is already linearly independent, then the dimension of W is equal to R. So you have the equality. Okay? So if we combine these two, this only says that if you have a linearly independent set, the span, okay, will be the set W, or If the span of that set is W, then the dimension of W is R. Again, linearly independent. If the set is not linearly independent, okay, if the set is not linearly independent and W is the span of that set, then the dimension of W is less than R. Okay? So that's these two statements. Questions? Now, example here, give all possible subspaces of R3. So I believe this will be my last example for this lecture. So anyway, give all possible subspaces of R3. So what are these subspace? Definitely, you have your R3, okay? This is your vector space. You know that the R3, this is always a subspace of itself, okay? So this is one of the subspaces. Another subspace is the space containing the zero vector only. This is also a subspace of R3. So you have the second subspace. What are the other subspaces of R3? So for number 3, let V be any non-zero vector, non-zero vector in R3. Then the span of V, okay, this is a subspace of R3. The span of V, this is of the form TV, where T is any real number, or T is a scalar. So this span is a subspace of V. Okay. Number 4, let V1, V2 be non-collinear. The non-collinear vectors in R3. Vectors in R3. Okay. Then the span of this set, or these two vectors, then span of V1, V2, this is also a subspace of V. But the span will be something like T1, V1 plus T2, V2. Here, T1 and T2 are real numbers. So this guy here is a subspace of V. Okay?